Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to come up with a form of Gauss's law for dielectrics. So let's begin with plain old Gauss's law. Gauss's law tells you that the electric flux through a closed surface is equal to the total amount of charge enclosed by the surface divided by the permittivity of free space, epsilon naught. Well, since we're dealing with dielectrics now, we also not only have to consider the free charge, but also the bound charge as well. And it's convenient to break this into two parts. Enclosed charge is equal to the free charge and the bound charge. So the free charge is the charge that we dealt with before when we handled problems that had conductors with a specified charge on the surface, and then also for specified charge distributions throughout a volume as well. A bound charge is what we've been dealing with lately. So bound charge means refers to the charge that's tightly bound to atoms. So let's consider a dielectric medium. And let's suppose that within this medium, a couple of conductors, generally speaking, you might have n conductors, but we'll just write down two conductors for brevity. And we'll suppose that there's some Gaussian surface that encloses both of these two conductors. The first conductor bears charge Q1, the second conductor bears charge Q2. And notice that I've drawn my Gaussian surface inside the dielectric itself, not outside, and not at the boundary. Free charge in this case, in this system, is just equal to Q1 plus Q2. The amount of charge, bound charge, is given by this expression. So we have the bound surface charge density contribution, and we need to take account of all the surfaces. In this case, we've only got two surfaces, S1 and S2. Now you might be saying to yourself, well, wait a minute, what about this surface S? Well, there's no, this isn't drawn at a boundary or a physical boundary. It's just a surface that's drawn within the dielectric medium itself. So there is no bound surface charge density on the surface S. Let's consider this term. This is over the entire volume contained within the Gaussian surface. I'm going to write these bound surface charge and bound volume charge densities in terms of the polarization. And the bound surface charge density is just the dot product of the polarization and the normal to the surface. And the bound volume charge density is minus the divergence of the polarization. I'm going to make use of the divergence theorem to convert this volume integral into a surface integral. Well, we're going to look at all the surfaces that bound this region of space. So clearly S1 and S2 are boundaries, but so is surface S. So again, to make clear, in the first case, we're looking at the bound surface charge density. And that kind of surface charge density will appear on the surfaces S1 and S2. Surface S just represents our Gaussian surface. Over here, in the second integral, we're taking at first the volume integral of the minus the divergence of the polarization, and then using the divergence theorem to convert this integral into a surface integral. So that's why we have S1 plus S2 plus the the surface S as well, and a minus sign. So you see what happens here. The contributions from the surfaces S1 and S2 cancel out. And we're left with minus the surface integral of the dot product of the polarization and the normal. I'm going to incorporate this expression into Gauss's law. I'm going to leave the free charge just as free charge rather than writing it out in terms. And then for my bound charge, I have minus the surface integral of the dot product of the polarization and the normal. I'm going to move this term over to the left-hand side and multiply through every term by epsilon naught. And I'm going to use another term to designate this quantity in parentheses. I'll call this D, and that is the electric displacement. And actually, there should not be an epsilon out over here. Okay. And this is Gauss's law for dielectrics. And notice the similarity in form to Gauss's law, where Gauss's law tells you that the electric flux through a closed surface is equal to the total enclosed charge. Here, we've introduced a new term, the electric displacement, and the dot product of the electric displacement and the normal integrated over a closed surface is equal to the total amount of free charge. So this is a convenient form because we're separating out the free charge from the bound charge, and that will make handling problems a little bit easier. Another convenient form for this is in differential form. So I'm going to convert this left-hand side to a volume integral using the divergence theorem. And over on the right-hand side, I can write the free charge as a volume integral. I can write it as the integral over the volume charge density. And I realize that this expression has to hold for any arbitrary volume, so therefore, we wind up with the divergence of the electric displacement is equal to the free volume charge density. Okay? So again, notice the similarity of form between Gauss's law and we'll just call that Q enclosed over epsilon naught and Gauss's law for dielectrics. Let's look at a few examples. Now, just recall from when we first started talking about Gauss's law, there really was a limited number of types of problems that could be solved. The problems had to exhibit a certain amount of symmetry. So in other words, we handled problems where you had spherical charge distributions that were spherically symmetric. We had dealt with spherical conductors. We looked at very long line charges. We looked at charge distributions that were cylindrically shaped that had cylindrical symmetry. And we also looked at infinite charge sheets as well. So those same limitations apply when you're handling Gauss's law for dielectrics. Problems in question have to have that kind of symmetry. So let's take our first example. Let's suppose that we have a very long wire. And let's suppose further that it is surrounded by a dielectric sheath. And we'll suppose that the radius of that sheath is capital R. I want to apply Gauss's law for dielectrics to figure out what's the electric field, what's the displacement, and then what's the electric field. Okay. Now, keep in mind we're considering where it's so long that the end effects can be ignored. So you choose a Gaussian surface such that the displacement is constant over that surface. In that case, you can pull d outside of the integral. And when you have a cylinder, you choose a cylindrically shaped Gaussian surface. Whether we look inside the sheath, inside the dielectric, or outside, the expression on the left-hand side will be of the form 2 pi s, where s is the radius of observation, times the length times d. Over the right-hand side, the total amount of free charge enclosed by that is equal to the line charge density times L. Cancel the L's out. And the electric displacement goes as the line charge density divided by 2 pi s, where s is the radius of observation in the radial direction. So regardless of whether you're inside the sheath or outside, the displacement is going to have the same value. Now what's the electric field? That's what we're really after. Well, you know, the relation between displacement and polarization and electric field. So the displacement is equal to epsilon naught times the electric field plus the polarization. So outside, the polarization vanishes. We're outside the sheath. P equals 0 there. And so therefore epsilon, or rather E, is just equal to lambda over 2 pi epsilon naught s in the s direction, in the radial direction. That's the same answer we got before. In this case, the dielectric sheath isn't shielding anything. We just wind up with the same answer. Now what about inside the dielectric? Surely that's going to have a different answer. And it will. However, it's a big however, we're not given the polarization in this case. We don't know what it is. So that's a question mark. You don't know what the polarization is. You know what the displacement is, but that's unknown. Unfortunately, in this case, electric field is also undetermined because we weren't given enough info. Okay? But in spite of the fact that there was no specific information about what kind of dielectric it was, what this polarization looked like, you can actually glean a little bit of information about what the electric field is going to look like, however you are limited to the exterior region. Okay? Now let's look at another problem where you actually are given what the polarization is. let's suppose that you have a dielectric shell. There's no free charge, and the inner radius of this dielectric shell is RA, and the outer radius is RB. I want to figure out what's the electric field everywhere. I'm going to solve this problem a couple of ways. I'm going to first solve it using plain old Gauss's law. And then I'm going to handle it using Gauss's law for dielectrics. So let's suppose the polarization in this problem is equal to K, where K is a constant times the radius. In order to apply Gauss's law, I need to know the total amount of enclosed charge. There are three regions in this problem. Inside the cavity in the shell itself, and outside the shell. So in other words, we've got R less than RA, R greater than RA but less than RB, and R greater than RB. If we apply Gauss's law, we need to figure out explicitly what's the total amount of charge contained in each of these three regions. In the cavity itself, if I construct a concentric Gaussian surface, there's no charge in there. There's no free charge and there's no bound charge. So immediately, charge enclosed vanishes, and therefore E is equal to 0 there. Now what about inside the dielectric shell itself? Well, I do need to figure out what charge is contained. There are two surfaces. There's the inside surface at RA, and then there's the outside surface at RB. On the inside surface, P dot N is just going to be minus K, RA, and the outside surface is going to be K, RB. And the reason why there's a negative sign is because the normal to that surface is going to be pointing inwards, and on the outside surface it's just going to be pointing out from the dielectric shell. So that's why that's positive. We will have a volume, bound volume charge density. And that'll just give me minus 3K. Now to figure out how much enclosed charge we have, well, if I look at this surface drawn inside the shell, it contains surface charge density on the inner surface, but not the outer one. So I'm only going to have a contribution from the inside. And as far as my volume goes, I'm going to start at RA, and I'm going to integrate up to some radius R, where R is somewhere in between RA and RB. The first term is going to give me minus K R sub A. Sigma B is constant over that surface, so I can just calculate the surface area of the inside, and that's just going to be 4 pi RA squared. And in the second case, we'll be integrating over the volume of this from the inside surface of the dielectric shell to some point at some radius r. The angular integrals are just going to give us a factor of 4 pi. And the volume charge density is constant throughout, so it's just minus 3K. And last but not least, we integrate the radius over the radius. That's going to give us r cubed over 3. And we're evaluating this from RA up to R. So the contribution from the bound surface charge density actually cancels out this term RA that we obtained from the volume charge density. And you're left with the total amount of enclosed charge is equal to minus 4 pi k over r cubed. Okay. Left-hand side, again, because we're constructing a Gaussian surface concentric with the shell. E is constant over that surface because of symmetry. So we wind up with 4 pi little r squared E. So if I set this equal to this, I wind up with the electric field is equal to minus K R over epsilon naught. And look at the relation between the polarization and the electric field. The electric field is equal to minus polarization over epsilon naught. Okay? And one final section. For the region outside, what's the total amount of charge? Total enclosed charge. Well, you could do the math explicitly, or you could just realize that for whole dielectric medium, the charge must be neutral. So Q enclosed is equal to 0. And I encourage you to work this out if you don't believe me. So in other words, this interval is going to go from little RA up to RB, and then you'd have an additional term due to that surface. Okay? So we add this, the total amount of charge is going to vanish. But anyway, let me just erase that for now, so I don't muddle the two problems. Anyway, since the total enclosed charge is equal to 0, the electric field must also vanish. Okay? Now, it actually took a lot of work to arrive at this answer. In fact, there's a shorter way of doing it. And the shorter way of doing it is to apply Gauss's law for dielectrics. The total amount of free charge in this problem is 0. So therefore, the displacement vanishes everywhere. So D equals 0 everywhere. It's a little superfluous. So what does that tell you? In the region R less than RA, because the polarization vanishes there, E is equal to 0 there. Outside, polarization is equal to 0, and E is equal to 0. In the region, in the shell itself, Polarization is equal to constant times the radius. And if we make use of the relation between the electric field, the displacement, and the polarization, see right away the electric field is simply equal to minus constant times the radius over epsilon naught. That was exactly the same answer we got before, only with a lot less work. So there are certain problems where it's far more convenient to use the displacement, basically use Gauss's law for dielectrics, than it is for the electric field. However, there's a big fat caveat. And just leave it up there for one more minute so you can take everything in. And the big fat caveat is that whereas before I said that Gauss's law was entirely equivalent to Coulomb's law, okay? Gauss's law on the left-hand side, Coulomb's law on the right, okay? Now we get Gauss's law for dielectrics. It is absolutely not true that there's a kind of Coulomb's law for dielectrics, or for the displacement. This is wrong, 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 okay? So no Coulomb's law. For displacement. And the reason for that is that the displacement isn't just a function of the free charge. It's not just the case, well, okay, we can just throw away the bound charge, forget about it, and then, just take care of the free charge, work the problem, there you go. No, the free charge, as I mentioned earlier, is influenced by the bound charge. Now, you have that relation between the electric field, the polarization, and the electric displacement. So when you look at the Coulomb's law, this is all the charge, okay? This is a free charge and the bound charge. This contains a free charge and the bound charge. This contains a free charge. However, the free charge is influenced by the medium in which it's embedded. So you can't just say, well, I'm going to pull everything out, just forget about the bound charge and just do the math. So, important thing, there is no Coulomb's law for the displacement. Now, the problems we worked, there was inherent symmetry in them. So this wasn't an issue, okay? But if you look at this relation, not only do we have the divergence of the electric field is equal to the amount of charge over epsilon naught, the curl of E also vanishes. So curl of the electric field always vanishes. But the curl of the polarization doesn't always vanish, and that means that the curl of the displacement doesn't always vanish either. So just keep that in mind, and you won't find yourself running into grief. Next time I'm going to go cover a couple of problems where we talk about linear isotropic medium, and I'm going to apply Gauss's law in those situations as well. Okay? Well, so that concludes today's lecture.